Okay. Hello, everyone. Welcome. Let's wait 15 seconds in case there's some people still joining us. And because it's already 3 o'clock, I think we should we could start. So it's a great pleasure to have Germán Gieczewski here today from Princeton. The title of the presentation is Noisy Screening and Brinksmanship. So as usual, our talks are 1 hour. That includes questions and answers. If you have any questions, you can wait till the end. We'll reserve 5-10 minutes towards the end. But if there's anything pressing or clarifying questions, you can ask during the talk. The talk is recorded, and once we stop the recording after 1 hour, please stay. If you have any other questions, we can stay for a few more minutes. And just as a reminder, in 2 weeks, we meet in 2 weeks on the 2nd of June. Ding Yang from Michigan is going to present Ancient Epics in the Television Age, Mass Media, Identity, and the Rise of Hindu Nationalism in India. Okay, Germán, the screen is yours.
All right, thank you. Thanks, everybody, for coming. And I apologize in advance for any incoherence because I have a 3-month-old baby at home. And so my brain is like, okay, here we go. So, this project is about encroachment, I guess. My initial motivation to start thinking about it was a question from international relations, which is sometimes you have these interactions in which you have, let's say, two countries that are rivals. One is gradually making more aggressive demands of the other, or making, more taking actions that are like fait accompli that, keep escalating over time. And eventually, sometimes that leads to, the rival eventually saying at some point, okay, stop now, we're going to have to fight the war. Right. And exposed, this looks like a really costly outcome that doesn't seem like it benefited anybody, perhaps. Um, and So I guess one framing for the project is just, why does this happen? What's the most natural model to think about? So I'm going to think about a model in which you have an adversarial relationship with lopsided initiative. What I mean by that is we're going to have two players, one that can repeatedly sort of change the terms of an agreement, and the other one that has a more coarse instrument. So basically, they can either acquiesce and let the interaction continue, or they can say stop, and that's permanent, right? So you can think, international relations. So I mean, I keep invading islands, or I keep, invading neighboring countries, or whatever it is, and then you can choose to launch a war or not in response. I'm going to assume that the receiver has some private information about their payoffs, which implies some sort of breaking point, right? Basically, there's some point beyond which if you go, then you can expect that the receiver is going to reject your demand, but you don't know where that point is. And one concern for the receiver here is that every time that you acquiesce to a demand, not only may you not be super happy about what you're agreeing to, but also you're giving the proposer information about what you're willing to agree to that he could, in principle, use in the next period. And then think, oh, well, he agreed to this, so I'm going to ask for even more tomorrow. And then if he agrees to that, I'll ask for even more tomorrow, and so on and so forth. Right? So the question is, would that happen on the equilibrium path? Under what conditions would it happen on the equilibrium path? What kind of model do you need to get that result? So, if you want examples, I guess the most obvious one is the lead up to World War II, right? Germany took several actions like remilitarization, in contravention of the World War I peace treaty, and then, annexed Austria, part of Czechoslovakia, the rest of Czechoslovakia, and then invaded Poland. And at each step, Hitler learns more of Chamberlain's willingness to appease, right? So basically, each time he makes a demand, he's like, oh, they give up pretty easily in that. So, he thinks, oh, maybe in 6 months I'll ask for more, right? And there's a telling quote that he said to people in a meeting shortly before invading Poland. He said, our enemies are little worms. I saw them at Munich, where the Sudetenland was conceded. So basically, the point of the quote is he's arguing that because, of behavior that these people showed in response to demand to take part of Czechoslovakia, he can infer that the Allies wouldn't go to war with him over Poland. Right? Of course, he ended up being wrong about that, but the point is that he attempted to draw that sort of inference, right? So you can give other examples, also other contexts. I can talk about this if people are curious, but you can imagine a worker that's being exploited by an employer that each day says, okay, you need to do this much work, otherwise you're fired, and then just keeps asking for more and more. It's the same logic. Or you can think of a multinational mega tech company like Microsoft or Google that keeps going further and further into taking actions that you think are eventually going to lead to antitrust action or regulator action that they probably don't want, but they still keep pushing until it happens, right? Okay. So how does the model actually work? So there are two players. One I'm going to call the proposer, the one that sets the demands. The other, the receiver, is the one with private information that can terminate the game. In each period, the proposer makes a demand. That's basically splitting a pie. The receiver can accept and continue the relationship or quit and take an outside option, which permanently ends the game. The receiver's outside option is persistent and privately known. So there's going to be a theta that's drawn at the beginning of the game, never changes. But we're going to assume, and it's going to be very important, that the receiver's willingness to accept also deviates from that persistent outside option slightly from period to period. Essentially, it's almost as if your willingness to accept is going to depend on a parameter theta plus epsilon t, where epsilon t is going to be redrawn each period. So the logic for this, you can imagine if we are in the international relations context, it could be something like, well, in some periods, it would be slightly more or less costly to fight a war because of my readiness, or my audience cost will be higher or lower because there's an election coming, or something like that. In the case of an employee that's being exploited, you could imagine that, oh, well, my alternative job offer is slightly better or worse in each period, and so on and so forth, right? Okay.
So, Germán, can I ask a clarification here? So essentially, instead of having a randomly changing outside option, you have an outside option that's fixed except for a randomly changing small component, and you're gonna make that small component, I suppose, you're gonna take limits in some sense on that thing. Is that
I'll be interested in that. Yes.
Yeah. Okay. Okay.
So are you wondering, because I guess one question that I get, and I don't have as much of an answer as I should yet, but is why don't you just assume something like a Markov process instead of this, right?
Mm-hmm.
It's possible that some of the results translate to that case, but basically it will be easier to do it this way so that there's a clearly demarcated persistent component theta that the proposer is learning about over time as the game continues, right? And so it's easier to do it that way than to.
Okay, so let me rephrase my question. Do we want the persistent component to be essentially that plus some epsilon that's going to be arbitrarily small, or do we want to just distinguish between a persistent and a changing component, and that you're not really thinking about the changing component being arbitrarily small? It could be quite large. I don't know. You haven't told me about any boundaries or something.
Yeah.
Which one of these two are we? Because there are two different assumptions, I think.
Yeah. So I mean, in principle, the results tell you things about both cases, but I'm interested more in the first case, I would say.
Okay. All right.
Yeah.
Okay. Thanks.
Okay. So one question you might ask yourself is why even have these shocks? So the answer is that there's this paper by Tirol, that's in Econometrica 2016, that studies basically the same exact problem I described to you without the shocks. So it's a model where the receiver's type is completely persistent, right? And his main result is that surprisingly, you don't get any encroachment in this model, which means that the proposer plays the same strategy as in essentially the one-shot version of the game and never escalates further. So you can calculate an optimal demand that sort of trades off, the fact that if you make a higher demand, more taps are going to reject, but the taps that accept are going to give you higher payoff, right? So there's some optimal, solution to that one-shot problem. It's basically like monopoly pricing. And it turns out that in the Tirol paper, even if you have more periods, And even though there's this learning happening, the proposer's optimal strategy is to make that same demand in every period. And so there's no escalation. Whatever receiver taps quit, they quit in the first period, and then after that, essentially nothing happens, right?
Can I ask a question? Because I'm sorry to interrupt again.
No worries.
Certainly with commitment, how is this different from a general principle that if you don't have any new if a game is theoretically dynamic, but if information is static, you might as well do everything as soon as possible. I suppose this is Tirol's paper. I'm asking this question to, not yours. But maybe without commitment, I don't know. I need to think about it. But certainly with commitment, that would seem to be. I mean, isn't this obvious, or is it? Why I'm missing something? Obviously,
let me think for a second. So his result is true both with and without commitment, but actually, so with commitment, so I'll show you the exact result in a moment. But basically, without commitment, it's true regardless of discount factors. With commitment, it's true when the proposer is weakly more patient. But it's actually false when the proposer is more impatient. And essentially the reason is that in that case, there's a backloading strategy where you make it so that the receiver pays you back. The receiver gives you higher payoffs early on, and you commit to giving him good payoffs later on. But that's actually the reverse of escalation, right?
Yeah.
Anyway, so I agree. Some people think this paper is deep. Some people think it's trivial. So.
No, I wonder whether I hadn't legislated for having different discount factors that might actually explain it. I don't know.
I guess the other, but I guess maybe the other answer is the commitment version of the problem is not necessarily equivalent to a principal agent problem in which you're like essentially getting the guy to reveal your type in a message at the outset and then you do whatever. Because fine. So I guess, the thing that's different is that the proposer will always learn from the receiver some information about the type when a demand is accepted. And also, if a demand is rejected, the game ends, right?
Okay.
So that imposes some constraints on.
I'm sorry, I'm wasting your time because I'm
no. Okay. All right. Fine. Let me keep going. So fine. So I guess the short answer then is, well, this paper maybe surprisingly, maybe trivially shows you if you don't have these shocks, then there is no encroachment, which is kind of unsatisfying, at least to me. And it turns out that if you have these shocks to the receiver's willingness to accept, then you do get encroachment. By which I mean proposals become more aggressive over time, and under some conditions I'll show you, exit is in fact inevitable in the long run. And I will also give you some results on the speed of encroachment when you have essentially big jumps or like slow gradual escalation and so on and so forth. So what's the intuition for why these small shocks will return the result and give you escalation? So you can imagine that given a certain demand, without shocks, there's some set of receiver types high willingness to accept, and they're going to stay in the game, and then the people below that are going to vote, right? In the model without shocks, if you've made such a demand, you've basically screened out these receiver types, you are keeping these, and then if you make the same demand tomorrow, all of these people are going to accept. In the model with shocks, even if the shocks are small, if you've already made some set of receiver types quit, then there is still some demand you can make that will be accepted for sure, but you need to make it slightly lower than the demand would be in the model without shocks, because you basically need to hedge for the shock, right? Essentially, if you make a demand that's equal to the willingness to accept of the marginal type in the absence of a shock, but he gets a bad shock, then the guy will quit, right? So the point is, if the shocks are banded within a small interval, you can always just reduce the demand by the size of the support of the shock, and then you guarantee acceptance, right? But then what happens if instead of doing that, you say, let me ask for a little bit more than that? Well, what's going to happen is you'll only get punished, as in the receiver will only quit if he has a marginal type or close to marginal, because if his type is much higher than whatever the threshold was for acceptance in the previous period, then he's not going to be close to rejecting anyway. And the other thing that you need to get punished is that the shock realization needs to be unfavorable. Because if the shock realization is favorable, you sort of get lucky and still don't get punished. And it turns out that the probability that both of these events will happen for small escalation is second order. So basically, it's like if you ask for epsilon more than the highest demand that's accepted for sure, then the probability that the receiver quits in response is like epsilon squared times some constants. And so there's always a temptation to try to go a little further. And when you do that, at least sometimes you will ex post learn, oh, look, the receiver accepted this demand. That means his type is actually higher than the threshold in the previous period. Once I learned that, the posterior distribution of receiver types in the next period is different, which means that I will then want to escalate even more. Okay? And another way of thinking about this is that because of the shocks, whenever the receiver accepts to, acquiesces to a certain demand today, I also learn a little bit to how he might respond to different demands tomorrow. So this kind of matches this logic that, well, if I see how I respond to my demand over Czechoslovakia, then maybe I know something about what you're going to say about it, right? Okay. Literature, there's quite a bit. So there's a paper by, there's some papers in the crisis bargaining literature and international relations within political science that think about these problems of like someone making a demand and then the receiver having private information, but also the option to go to war instead of it just being an ultimatum game where the receiver has no leverage. Most of these models are static. There's a few dynamic models. There's one that is pretty close to a Tyrol model, but that's about it. There's a large literature on the Coase conjecture. As you know, this model smells like the Coase conjecture, but it's sort of in reverse, because in the standard Coase conjecture model, essentially when the receiver accepts, that means that he buys the good and then the game ends. When he rejects, the game keeps going. And so that means that when the game keeps going, you learn negative information about the receiver. You learn, oh, this guy must not have a high valuation. That's why he rejected my offer, my price. So I have to make him a better offer tomorrow. Whereas in this setting, you think, well, if he's still in the game, then maybe I can take more from him, right? So there's the Tyrol paper and a couple of follow-up papers that are about positive selection, but they don't study this case of shocks that sort of add opaqueness to the receiver's decision, and hence, these papers don't have the results I'm going to show you. There's also a paper that does essentially Coase conjecture with agenda setter model payoffs, Romer-Rosenthal payoffs. There's also another literature on escalation that relies on a totally different assumption, which is endogenous outside option. The logic being something like, if I ask to take some of your land, your payoff may go down, but also your outside option, your ability to fight me in the future also goes down. And so under some conditions, you have paths of escalating demands that take advantage of the deteriorating outside option. And also, I guess this smells a little bit like ratcheting, in that you are sometimes learning something about the receiver's type and using that to ask for more in the future, right? But ratcheting is different in that the receiver has more leeway to basically just not work, pretend that he can't do the job or whatever, but the game doesn't have, right? Questions before I do the model? Okay. So time for most of the presentation, it's discrete and infinite. 2 players, player 1 is the proposer, player 2 the receiver. Discount factors, delta 1, delta 2. I will sometimes want them to be different. In each period, player 1 makes a demand that I'm going to call xt, non-negative, leading to flow payoffs xt and minus xt minus epsilon t if accepted by player 2. So I ask for xt. If player 2 says yes, player 1 gets xt, player 2 has to pay that, and also they have to pay this epsilon t, which I will tell you about shortly. And if player 2 accepts, these flow payoffs accrue, and then we go to the next period, right? If player 2 rejects, then she takes an outside option and the game ends. So the continuation payoffs are going to be 0 for player 1, for the proposer, because his demand is rejected. Future demands are also rejected. He doesn't get anything. And for player 2, the payoff is going to be essentially minus theta per period. So with infinite horizons, just minus theta over 1 minus delta 2. The theta is drawn from a CDF capital F with some support. We assume bounded, with the bottom positive and continuous density little f. And we're going to assume that theta is persistent and privately observed by player 2 at the beginning. Okay. And so what are these epsilon t's? The shocks are IID drawn from a CDF capital G that satisfies either one of the following assumptions. For most of the talk, I'm going to use the first one. So the assumption says G admits a density little g that's symmetric around 0. We support minus eta to eta, and the little g is continuous restricted to the closed interval minus eta to eta. Right. So this could be uniform, could be triangular, could be any continuous function between minus eta to eta symmetric around 0. Right? And it does not have to be continuous at the boundary. So in particular, that, for example, means you can do uniform. Right?
So Herman, can I just a quick question to clarify? So basically,
Yeah.
so your review suggested that your results are not going to be continuous with respect to eta. So when eta is equal to 0, the equilibrium changes drastically. Is that?
Yes. Yes. So the assumption has a free parameter eta. Yes, and if you set the eta equal to 0, then we're back in the troll problem.
Okay, thank you.
There are interesting questions. There's going to be a sense, for example, in which the equilibrium path is this. For example, I think the demand path is continuous in each period, but the tail behavior is discontinuous. So it's like if you compare the xt that's demanded by the proposer, that's going to vary continuously in eta, including at 0, but the limit is not continuous at 0. So you can imagine something that like escalates, but escalates more slowly as the eta goes to 0. And so when you go all the way to 0, suddenly there's no escalation.
All right, thank you.
Yeah. Long time no see, by the way.
Yeah, likewise.
Okay, so model. Timing in each stage. First, the xt is announced. So the proposer chooses xt, is shown to the receiver, and then the epsilon t is drawn by nature, seen by both players, and then the receiver accepts or rejects. And then, either the game ends or the game continues in the next period. Solution concept is perfect Bayesian equilibrium. Here, I'm assuming the epsilon is revealed after the proposer's demand is made, but before the receiver makes their decision and is seen by both players. If you assume that the epsilon t is seen by the proposer only at the end of the period after acquiescence, then it's the same exact thing, right? Because the proposer doesn't get to make another decision until the next period. So you could imagine something like, well, if the receiver accepts, then I get to see Sonia's costs ex post or something. Right? Now, an alternative assumption you could make that's a little more different is you could assume that the proposer never sees the realized shocks, right? I can infer something from the receiver's behavior, but I never actually get to observe them. This is similar. Many results are similar. And in fact, I wrote the whole paper that way. And then I decided it was better to switch. So now I'm doing this way. The main reason is that the no commitment case is less tractable when you never see the shocks. And the conceptual difference is that if you don't see the epsilon t, then the updating is different. Essentially, when I get to see the epsilon t exposed, I will know, given the receiver's equilibrium strategy, something like, well, a type theta would have accepted the demand that I made with these shock realizations and not with these. And so after I see, knowing the demand that I made and knowing the shock that was realized, I would know exactly what thetas would have accepted or rejected. So basically what that means is that in the specification I'm showing you today, at the end of each period, the proposer's posterior about which receiver types are still in the game is always going to be a truncation of the prior. It's going to be every theta above some theta star, right? Which depends on the EX that I demanded and also depends on the epsilon that was realized. If I don't see the shock, then I would have some interior probability for some thetas I would think, well, they may have accepted, they may have rejected, depending on the epsilon that was realized, which I don't see. And so calculating the posteriors is more difficult. Got it. So what's a one-shot benchmark? Let's say that you have the one-shot version of the model with no shock. So this is just what is the canonical crisis bargaining model in international relations. So the solution is very simple. Player 2 accepts the proposal if and only if theta is more than x. Remember that my payoff if I reject is minus theta per period. There's only one period here. If I accept, it's minus x minus epsilon. There's no epsilon, so it's just minus x, right? And so if my theta is more than x, I accept. If it's less, I reject. So then player 1's payoff from a demand is, if I demand x, I get x, and I get it with this probability 1 minus f of x, right? Probability that the theta is above x. And so the optimal x solves the first order condition. That's basically that u prime should be equal to 0, assuming that we're not at the corner solution. And if you have increasing hazard rate, then there's a unique solution to this. So this is all very well known. So what happens in the Troll model? So this is the dynamic model, so with more periods, but still with no shocks, with the epsilon set to 0. And so this is a summary of the results in the Troll paper that says, without commitment for any delta 1, delta 2, in the unique perfect Bayesian equilibrium, the proposer sets the xt equal to the x hat, the solution to this first order condition for all periods. Right? So this is a sense in which the solution is the same as a one-shot solution. And when there is commitment power, if the proposer is weakly more patient, then he can do no better with commitment power. He still does the same thing. On the other hand, if he's more impatient, then he can backload payoffs, which is essentially reverse escalation, right? He makes like lower demands over time. Okay, so this is basically what the solution looks like. In the Troll model, some demand is made, then this is some part of the distribution of receivers below some threshold reject right away, and then the ones that don't reject right away acquiesce forever because there's no further escalation. Okay. So what happens in the model with shocks? I'm going to start with the case of a perfectly impatient receiver, and I might only get to show you that case. We'll see. But this is the case in which the logic is simplest. And as you've seen in the case of no shocks, the Troll result goes through, which is basically that with or without commitment power, the proposer's behavior is just demand x hat in every period. So what we get here is, suppose infinite horizon, delta 2 is 0, and G satisfies the A1 of eta for any eta. Oh, forgot to say, I'm so sorry. So I said there are two versions of this assumption. So the second version of the assumption adds the additional constraint that it should be continuous at the end of the support. So basically rules out uniform or anything like that that has to drop where support ends. But for now, I don't need this. So let's say that we have the more general assumption. Then the proposer's problem is the same with or without commitment. And in any equilibrium with or without commitment, every receiver tap below theta hat, which is the top of the support, eventually equals with probability 1. Okay. So you see that this is very different from what happens in the Troll model. So let me tell you why this is true. The impatient receiver accepts the demand xt at time t if theta is more than xt plus epsilon t, right? Remember, theta is what I pay, is my cost if I reject, and my cost if I accept is xt plus epsilon t just by definition, right? Of course, if I continue the game, there's also the difference that if I accept it, there's also a difference that I continue the game, so tomorrow more things will happen. But since the receiver is perfectly impatient, he just cares about flow payoffs today, so this is all he needs to think about. Right? Okay. So the fact that commitment power doesn't matter, it just follows from the fact that the receiver is basically an automaton in this case, right? He just accepts or rejects based on how xt plus epsilon t compares to this. And so you can just imagine the problem as the proposer is just facing a machine that accepts or rejects demands xt based on this rule, right? And there's some, there's some dynamic programming problem to this, like solution to this problem, right? Here comes the part where we get to use the fact that the shocks are observed by the proposer by the end of the period. What does the proposer know about the distribution of receiver taps left in the game? At any history HT, the proposer knows who will still be left in the game. It will be the players with theta above theta t star, where theta t star is the maximum between theta t minus 1 star, the previous threshold, and xt minus 1 plus epsilon t minus 1. So basically, I will know that the thetas left in the game will be those that are above the max of all of the x plus epsilon realized in previous periods, right? I know exactly what thetas are left in the game. Right? Okay. And so in principle, strategy for the proposer would have to take the form xt as a function of the history, right? So basically, I know that all past demands have been accepted. I would have to be able to condition all the epsilons, but it's not too hard to show that optimal strategies will be of the form x star of theta t star, basically that the only condition on what that threshold is, right? What is the population of receivers left in the game, right? Okay, so if you believe that, then we can set up the proposer's optimization problem as follows. We can say, let capital V of theta star be the proposer's Rayleigh function when the marginal receiver tap left in the game, assuming on-path behavior by the receivers, is theta star. Then V of theta star should equal the proposer's payoff from that period onwards when he makes the optimal demand X in that period. So if I make a demand X, there's some probability that the epsilon realized is less than x star, less than theta star minus x. When epsilon is less than theta star minus x, it means that x plus epsilon is less than theta star, which means that it means that type theta star wouldn't quit. And since he was a marginal type, no type above him will quit either. So that means that in that case, essentially, I've made a demand so low that no receiver types quit at all, right? So in that case, my demand will be accepted for sure. I will get X for sure. And then I will get delta 1 times the continuation value, which will be the same thing as this because nobody quit. So I'm in the same state. Now, with this complementary probability, I will get an epsilon above this threshold. And so for every epsilon between this threshold and eta, right, there's some probability, right, that I get that epsilon. So little g of epsilon is just the density of that epsilon being realized. And then, in that case, essentially, one of two things will happen, right? With these epsilons, my demand x plus epsilon is high enough that it's higher than theta star. And so either I will be facing a receiver type theta that is above my demand, or I will be facing a receiver type that is below my demand. If the receiver type I'm facing theta is below my demand, he will quit on me, right? And I get nothing. If it's above my demand, I will still get what I requested, X, but in addition, I will learn going forward, because I will see the epsilon, I will learn that the new type in the next period is X plus epsilon, it's longer theta star. So my continuation value tomorrow will depend on this. Okay. And the probability that I get this in this case is probability that theta is more than my current demand, given that it's already higher than theta. Okay? And then in the other case where theta is below theta, the X plus epsilon, the term just doesn't show up in the calculation because I'm just getting 0. Okay. So then I can rewrite this as just g of theta star minus x. Remember, capital G is the CDF. And then this I can rewrite using what I know about the distribution of theta. Okay. And there we go. So first observation, what happens if I choose an x that's below theta star minus eta? If I choose an x that's below theta star minus eta, then this probability will equal 1. Because even when the epsilon realizes eta, which is the worst case scenario for me, x plus epsilon is going to be, well, at most theta star minus theta plus eta, which is theta star. So basically, in that case, there's no chance that my effective demand, x plus epsilon, goes above theta star. Great. So in that case, I will just get 1 times x plus delta 1 v of theta star, wherever the x is. And so clearly among those demands, the best one that I can make is theta star minus eta. There's no point going below that. I'm just giving, free money to the receiver, right? And if I demand exactly theta star minus eta, my payoff, if that were the optimal demand, my payoff would be theta star minus eta over 1 minus delta 1, right?
Can I ask here?
So, yes.
So comparing this to what happens in the Tirol model, can you
Yes.
pinpoint like the place where it really doesn't transfer and therefore his result is different, or is it trivial of a
So I guess the Tirol model would correspond to having the G. So the epsilon would be identically 0, and that means the G would be a step function.
Yeah.
Right. So I think on the next page you'll see what's going to be different. Yes. So all I've said so far is, okay, if you make a demand below theta star minus eta, there's no quitting. You might as well go all the way to theta star minus eta. If that were the optimal demand, this would be the V of theta star. Now, that may not be the true value, but the true value has to be at least as much, because it's always an option for you, even if supposedly the equilibrium is something else, it's always an option for you to make this demand today and to then keep making the same demand in the future, and that will guarantee this payoff. So the V has to be at least as much. Great. So then I'm going to ask myself, what happens if I take x equal to theta star minus theta plus nu for a nu small enough? Then my payoff will look like this, or it will be at least this. So I'm plugging in x equal to theta star minus eta plus nu. So theta minus theta star plus eta minus nu gives me g of eta minus nu. Remember that g has support minus eta to eta, so this is almost g of eta, so it's almost 1. Okay? And then here I'm getting x, which is theta star minus eta plus nu, plus the continuation value. Remember, this is the term for the case in which I end up making a demand low enough that no receiver type quiz state does not move. And then with the complementary probability, 1 minus g of eta plus nu, I get some weighted average of what's in here, right? And the worst case scenario would be that basically whenever this happens, I get a shock equal to eta realized, so that the x plus epsilon is just theta star plus nu, right? In which case I get this expression. So basically, instead of taking the average over all of these, I'm just taking the maximum value, right? Of what this could be, and then in here, right, I'm plugging in the x, and then here I'm plugging in the worst case scenario, because this continuation value, when the x is when the x plus epsilon is higher than theta star, will result in the state going up, which is good for me, right? So it's risky for me, but when I try it and get lucky in the sense that I face a receiver whose step was actually high enough that he accepts, that's good for me in the continuation because I can make higher demands and get away with it, right? So a lower bound for my payoff is essentially assuming that I don't get to exploit that, at all. When I learn that the type is actually higher than theta star, my payoff will be as if, I'm still in state theta star. Right? So basically, this is the lower bound for the payoff that I will get when I make this higher demand. And now I can say, well, we said V of theta star is at least this much, right? And so then theta star minus eta plus delta 1 times this is just going to be the same thing, right? Theta star minus theta divided by 1 minus delta 1. And I'm going to have this nu floating around here. And then I'm going to have this, and then here I can also plug in that this is at least this much. And then delta 1 times that plus this also gives me this. And then I have a nu here that I'm just going to bound to 0, right? Okay. So bottom line, what's happening? Well, I have theta star minus theta over 1 minus delta 1 times this g, and then here I have it times a 1 minus g. So I can add those two terms and just get the same thing that I said was a lower bound for the V, but also had to be the exact value of the V if the optimal demand induced no quitting, right? And then I have this additional nu multiplied by this g. And then I have some leftover terms. So what are the leftover terms? Well, there's V times 1 minus G of this, but since the G admits the density, this G of eta minus nu is something like nu times little g of some maximum value, right? Or it's like whatever the maximum of G is, you can call it G upper bar. So this can be bounded by G upper bar times nu, right? And so I have a leftover term that's basically nu times G upper bar. And then from this term, I get another thing that's basically this is also something that can be expressed as G upper bar times nu. And then I have a leftover term from essentially this, right? So this I can write as 1 minus something that has to do with the gap between the theta star plus nu and theta star. But that I can also write as like f, the maximum value of little f times nu divided by 1 minus f of theta star, right? And so it's also something that looks like nu times some constants, right? So basically I can rewrite this whole thing as this plus nu minus nu square times some stuff, right? That's bounded. And we said if the optimal demand is low enough that there is no chance of escalation, then this will be my payoff. Then I said if I make a demand slightly higher, I get this. Clearly for nu small enough, this has to be higher than just the first term. And hence the conclusion is the optimal demand must be higher than theta star minus eta, right? And if the optimal demand is higher than theta star minus eta, it means that the probability that x plus epsilon is higher than theta star is positive, hence the probability of the state goes up is positive. And that happens in every state, which means that in every state, there's a chance that I'm going to go up and go up and go up. Right? So it requires a little bit more work to show that the gap between the x star and theta star minus eta is bounded away from zero. So basically, you could be worried, well, what if I'm sort of escalating, but the escalations are kind of converging to zero in some interior part of the support? Well, you have to do some additional work to show that's not the case, right? But that is also doable, right? Okay, so how is this different from Tirol? I guess when we write, this approximation here, what are the constants? One of the constants is the maximum of the density of this capital G. As you take the eta to zero, that G upper bar is going to infinity. So for any G that's not eta equal to zero, it's going to be some finite constant. And so this argument will tell you that some positive nu is better than nu equal to zero. But when you go all the way to the limit, that's not true anymore. So here's another kind of more hand-wavy intuition.
Sorry,
Theta star minus,
Germán,
yes.
I'm obviously missing something. So you can have a minus eta interval and a distribution on it that asymptotes at minus eta and minus, something like a U-shaped thing. I'm sorry, what is it that is stopping that from having towards the boundary will go to infinity? What's that stopping from being problematic?
Yes. Well, so the assumption that we made is the G admits the density G, support minus eta to eta, and continues on this closed interval. So that rules out
the closed interval. Okay.
Yes.
So you're not allowing. So you're not assuming anything like regularity but you're assuming a way. Okay, distributions that shoot up asymptotically. Okay.
Yes, and so so in particular, this means bounded. Yes. Yeah. Otherwise I would have problems.
Okay.
And I guess one kind of important version of that is if you assume something like the G is just binary, it's just like plus minus eta, then this doesn't really work.
Yeah, and beta distributions that have coefficients less than 1 have that property as well, I think. Okay.
Theta star minus eta is the highest demand that I can make that's guaranteed to be accepted. If I push a little bit beyond that by nu, for a small nu, this can only cause exit when the receiver's type is within nu of the theta star, and also the shock realization is within nu of the eta, and that has probability nu squared times some constants, right? So it's just like a less algebra heavy way of saying the same thing. Okay, so that's the first main result, and I won't get to show you much more, but let me tell you about other things that are in the paper. So the next thing that I try to do is figure out the speed of escalation, right? And essentially, you know what? Let me just do it with a picture. So the important feature that determines the speed of escalation is the shape of this function little u. Remember, it's the same function from the one-shot problem without shocks that we calculate just x minus 1 minus f. We said that in the one-shot problem without shocks, the optimal solution is to just make a demand that maximizes u, right? And what happens here is essentially that you will make a demand that basically moves quickly to screening out receiver types below the point where u is maximized. But once you get to such a point, you will still be tempted to escalate slightly, which leads to slow screening at the bottom of the distribution over time, right? If you ever get to a point where the u from that point onwards has some maximum at a higher x, right, that exceeds the current value, you will then jump there, and then you will keep going slowly like this, right? So that's the general pattern of escalation. That basically, if you're at a point where the u is higher than at any point to the right, then you'll escalate slowly. And if you're at a point where there's some higher x where the u is strictly higher, you will jump quickly, right? And then you will keep going slowly. And in particular, if you have monotone hazard rates, then you end up with a situation that looks like this, where there's one big jump, and then you have small escalation because the shape of the u in that case is single peak, right? And so you go to the peak and then you go slowly down. But if you have a u that's uglier, then you could have alternation between jumping and going slowly, and then jumping and going slowly, and so on.
This is
Okay.
in the limit, what you are just saying.
Yes.
Right.
So the proposition, yes, it's fine. So I am jumping over a bunch of things. You're right. So the formal statement is you have to take a sequence of eta going to 0, and for each one you take a g that satisfies the assumption for that eta, and then you take an optimal demand path under that shock distribution for each n. And then the formal result says if you have an interval where the u is increasing over that interval, or basically has a maximum somewhere to the right of that interval, then for n large enough, you never make a demand in that interval. That's the sense of you jump quickly through it. And if you are moving through an interval that's decreasing and that has no maximum to the right of it, that's higher than what you have within that interval, so it's what is called sunshine points, then for n large enough, you make arbitrarily many demands in that interval. And you can also basically use this result to say, well, given the interval, I can break it up into small pieces and it still applies to each piece. So you have arbitrarily many demands within each subinterval, as small as you want. Okay. And then when you are in an interval, we have slow screening. I have another result that basically gives you an approximate, it gives you essentially an asymptotic speed of screening when the shocks are small. So what the result says is, again, take a sequence of etas going to 0, gn satisfying the assumption for each eta, take path x n star of optimal demand for each eta n. Then if we're at a strict sunshine point, then gn of theta minus xn star theta converges to something. That's a function of parameters. So what is this? You may remember that g of theta star minus x is the probability that the receiver's demand, including the epsilon, ends up being low enough that there's no escalation whatsoever, right? So what this is giving me is a limit value for the probability that the demand made does not cause any escalation whatsoever in terms of screening out receiver types. With a complementary probability 1 minus this, we get an x plus epsilon that forces some amount of receiver types quit. course, how much depends on the exact value of the epsilon. And to get a formula, you need to know more about the distribution. But here's an example. If you assume that the epsilons are uniform, for instance, then you have a formula for the G that you can use to back out what this value for the capital G means for the value of the X star, the demand that's made, and hence for the speed at which you move, at which the state moves up, right? So this is ugly, and I don't have too much time to talk about it, but let me point out some interesting features. So it's proportional to eta. So that tells you is that as the eta, for example, goes to 0, the speed of escalation goes to 0 proportionally to eta, right? So essentially, the speed at which the X's are increasing and the speed at which the receivers are leaving is proportional to eta, at least when eta is small, right? It's also related to the delta 1, the proposer's discount factor. And when the delta 1 goes to 1, this goes to 0. And in fact, goes to 0 even more than linearly, right? It's a function of 1 minus delta 1 squared. But so the logic is basically the more patient the proposer is, the more worried he is that if I do this escalation thing, well, I'm getting some plus nu today, but I'm losing my entire continuation value when I get rejected, right? So that's more costly when I'm very patient, right? And it's also related to the hazard ratio, right? You can see that basically this is 1 minus f over theta times little f, which is hazard rate. Okay, I have 9 minutes, and I guess I should leave some time for like actual questions that are not just like, you know, what's happening on the slide. So let me tell you extremely quickly what else is in the paper. So what happens when you go away from the impatient receiver case? In the commitment case, the main problem is that now if you make a higher demand in period 100, the receiver may react to that by quitting more in period 100, but he may also quit more in earlier periods. Because maybe in period 70, he says, look, I thought maybe I would stick around for the option value of getting good payoff in period 100, but now I know that you cut that away, so I'm not going to stay in period 70. So that's the additional concern that the proposer now has when he attempts an escalation, right? And it turns out that when the proposer is more patient than the receiver, this effect doesn't matter enough to stop the proposer. But when the proposer is equally patient or less patient than the receiver, then it does matter and it stops escalation. And essentially the logic is, well, if the receiver is impatient, then in period 70, he's not going to react that much to what I do in period 100 relative to how much I care about getting a higher payoff in period 100, right? But when he's as patient as I am or more, then he does. And then what happens with no commitment when the receiver is not impatient? Well, now you would think that problem does not arise because even if, yes, when I make high demands in period 100, it's discouraging in earlier periods. Well, I don't care. You know, once I get to period 100, I'm going to optimize. And if I miss high demand, I make a high demand, right? So you think that it's more likely that I get escalation. But the difficulty is that now we sort of need to know more about the receiver's interpretation of deviations and what's going to happen afterwards. Because you think, well, if I went off path and I made a slightly higher demand, maybe that means that in future periods I will make much higher demands, where it's hard to know. So we need some discipline on what happens when you go off path. And so essentially you can solve for Markovian equilibria by condition on the marginal receiver type. And I have some results that basically say if you have the A2 assumption with continuity at the end of the support of the little g, then you still get the result of escalation that makes all receiver types quit. If you don't have it, then you still get the same result if we know that there's no discontinuities in the receiver strategy, but I don't have a great condition to check when that's true. And finally, even if I don't have any of that, just the base assumption A1 of eta, I can essentially give you a bound that says maybe you won't screen out all the receiver types, but you'll screen out up to at least some point that is a function of parameters. That's generally higher than we get in the one-shot case. Okay. It's 10:55, so I'm going to stop talking. And
thanks a lot. It's a great time anyway. Are there any questions? I have a question. You mentioned at a certain point, obviously you had a slide about the literature about cause conjecture, and you said it's kind of the opposite or inverted. So can you repeat that as well? And and also why why can't you use, or can you use the same trick but in reverse if it's a reverse argument?
So so in the standard cause conjecture, so the logic is that with that commitment, the proposer faces competition from himself, right? From his future selves, because it's like, well, if I make a demand and it gets accepted by some receiver types in the immediate future, I will know that only bad receiver types are left. Then I'm very tempted to make a lower, offer a lower price, but then that makes receivers in the previous period not accept. So here it's clear that this logic doesn't go through, right? If anything, you would expect something like the reverse logic. So the reverse logic would be something like, well, after a demand is accepted by some receiver types, rejected by others, if I go to the next period, I know that the set of receivers is in this higher interval. So I guess the question is, so I no longer face this problem of like, oh, I'm sort of undermining myself, right? But I guess what's not clear is, would I want to then make the same demand, or would I want to make higher demands, right? So I guess the point of the Tirol paper is that you will, in fact, want to make the same demand in the next period, right? And I guess one version of the logic for that is something like, I'm solving this monopoly pricing problem, right? The one-shot problem, right? Let's say that I made the optimal demand in the first period. Well, if I make that same demand in the second period, I'll get the same payoff again. If I make a higher demand, well, I'm just going to get the payoff from making higher demand on the optimal one in the one-shot model. There's no point in doing that. Yeah.
Thank you. Any other questions?
So Germán, can I ask? I am a little bit, so part of me thinks, okay, you really need this density, we discussed it, to be this kind of very technical but not easy to interpret behaviorally assumptions, right? I mean, for example, when we do mechanism design, regularity does have an interpretation that it's a technical assumption where we can understand. Here, for example, you need densities to be bounded and things like that. And I don't really have a sense of what an unbounded density differs from a bounded one in some way or whatever. Is it that, is there a way we could sort of think of a model where we get rid of these little technicalities that seem to really, I mean, you're doing that proof by using the maximum and so on. Couldn't you cut the thing above and say, I'm just going to cut it at some point. It's not going to be the maximum, but because the density, the mass of probability at those ends is small enough, let me just cut it here. The argument still goes through. Does that make sense? Do you see what I mean?
Yes. So if you're worried about that, I guess yes. So you could generalize to any G that is such that the density is bounded in a neighborhood of eta. So basically, in a neighborhood of the top of the support, you need the G to be bounded.
Yeah.
The density G to be bounded. If it has points where it goes to infinity that are not next to the top of the support, so if it does that at 0 or it does that at the bottom of the support, then it's totally fine.
Right. So I was thinking of exactly if it goes to infinity at the boundary, then you can just say, I'm not going to take the max because it doesn't exist. I'm just going to take some value, but the probability from that, so take that value, fix it, cut it up, then draw vertical lines down back to the support. then there's a distance between those points and the eta minus eta. If you make that maximum, that cut sufficiently high, the density in those things is from that cut above is going to be tiny. And then you can say, okay, this sufficiently approximates.
I see.
It's going to be greater than any. You can always find it such a way that it's greater than anything. So what I'm trying to say is certainly for the asymptotics that go to the boundary, I don't think it's a problem. And I think actually maybe this generalizes. So I don't think you need that assumption. I mean, it takes a bit more work, but I think you can get rid of that in your.
Yes, I'm thinking now as you're saying this, I think at the very least it's probably true that if the G even goes to infinity at eta, but I guess has some shape such that like the integral in the neighborhood of the eta is very small, it's probably still fine.
Right, and if it asymptotes, it must be small enough at some point, right? You just need that. You just need to fix a point. You don't. The only problem is infinity, but even if this is 10 billions, you can always cut it there. Yeah. Anyway,
Can you go it from the other side and say that the density is bounded from below, and therefore there's enough mass?
I don't think that works necessarily. Because I know that, for example, if you do something like, let's say that it's like, something like a combination of a uniform and then like discrete probabilities of the state being eta or minus eta, I think that does not work.
You do need continuity of a density, that's for sure, right?
I have a suggestion. Why don't we finish the official part and say the official goodbyes? So thank you very much, Germán, for accepting our invitation and for the great talk, and see you all in 2 weeks, and we can turn the